Hi, everybody. Thank you for coming bright and early, 9 a.m. on Monday. You guys are very well evenly distributed. It's very impressive. So I'm Anthony Scodary. I'm the co-founder of GridSpace, and we're going to talk about the challenges of scaling speech and language technology for the contact center and in general. We, in general, are a speech and language technology company. And we work in call centers as well as in capital markets, healthcare. But we are going to start with a movie.
Good morning. Thanks for calling Harper Valley National Bank. My name is Grace. How can I help you today?
Yes, last night I was entertaining some clients and I think I left my wallet at the restaurant, and to be safe, I want to replace my debit card.
Before I can help you with that, I'll have to authenticate you, okay?
Okay.
May I ask who I'm talking with first and last name, please?
My name is Chris Johnson.
And what was the name of your first pet?
Professor Sparkles?
Okay, great. That's Professor Sparkles. All right, let me check that information you gave me.
Okay, Mr. Johnson, just checking your name. Looking through your security questions.
Professor Sparkles. Oh my God, that's precious.
Oh, he was precious.
Okay, I just submitted your request. All right, thank you, Mr. Johnson. You are authenticated. Okay, should I go ahead and submit that request for your new debit card?
Yes.
Okay. Let's check on that card.
Just seeing how long that'll take.
Okay, so I expedited that brand new card A. I also went ahead and waived the normal fee for you.
Oh, thank you.
It should arrive in 3 business days, sir.
Great.
Is there anything else I can do for you?
Yeah, I should probably make sure no money was stolen from my old card. Can you tell me my checking account balance?
Okay, Mr. Johnson, I'm going to look up that checking balance for you.
Okay, bringing up your checking account. Okay.
All right, Mr. Johnson, I see here that your checking account balance is $37.35.
Okay.
Can I help you with anything else?
I would like to $1,000 from my savings to my...
Would you like help with something else?
Yes, I would like to transfer $1,000 from my savings to my checking account.
I'd be happy to make that transfer, Mr. Johnson.
Thank you.
Just to confirm, you want me to move $1,000 from your savings to your checking?
Yes.
Right?
Yes.
All right, Mr. Johnson.
I'm initiating that transfer.
Okay, Mr. Johnson, I submitted that. It should go through in 3 to 5 business days.
Thank you.
Would you like help with something else?
No, that does it. I appreciate it.
Okay, sir, have a great day.
You too. Goodbye.
All right, so what that demonstrated, that was a real capture of our dialogue system. Everything from the speech recognition to the speech synthesis to the dialogue system is all built at GridSpace. Even the telephony is built at GridSpace. And a system like this, what I want to underline is the amount of complexity to scaling a system like this. In terms of passive analysis, GridSpace in the last year analyzed around 2 millennia of conversational speech data for our customers. And scaling systems of this complexity, and especially when you add interactivity, presents a lot of unique challenges, which we'll be talking about. Specifically, what we work on at GridSpace, we work on interactive applications and passive applications for long-form conversational speech and language. And so the roadmap for this talk is we're first going to talk about some fundamental challenges that we face and that anyone working in this field will face as you start to scale and especially work in large speech environments like a call center. And then we have two case studies. The first from Wonkyum Lee about closed loop training in speech recognition systems. And the second case study is in reducing latency in speech synthesis on inference from Alex Barron. So fundamental challenges. So I have this on a 2x3 here. Along the top, we have time, predictability, and complexity issues. And then we have divided into things that you optimize for and things that you manage. We'll talk about all 6 of these and then in depth for a couple of them. So latency, obviously how long it takes for something to respond to stimulus. Stochasticity, how predictable a system is, whether we want it to be predictable or not. Scale, just handling tens of thousands of conversations at a time. Aperiodicity, things that are bursty, things that follow a diurnal cycle. Nonlinearity, things that are not linear, which we'll define more rigorously if you don't already know what that means. And then interactivity, things where there's a human in the loop, adding complexity. So latency. Latency is really important once you start entering the interactive domain, but it's also really important even in the passive domain when we're doing live speech analysis. Because oftentimes we want to present to, for instance, a call center agent, hey, like this very obscure topic was just discussed. Here's the very obscure response that our business leaders have dictated you should follow in the call center to optimize for this obscure case that we could not have possibly trained in your week and a half of coming up to speed as a call center agent. Latency, in general, exists between any interactive application, even just between two people having a telephone call. You have everything from the ADC and the devices to the encoding, whether it's G711, G729, the backbone delay, the PSTN delay, the jitter buffers, and all the other buffers that are in that path. We inherit almost all but maybe device playout in something like that dialogue system you saw demonstrated in the video. Plus, we add all these additional latency budget consumers like MSCC generation. There's half a dozen to a dozen neural networks running live in series to make an application like that possible. Interactivity obviously becomes more of an issue when you start to serve things like our dialogue systems, but in general is important when you want anything to be snappy. And so here's a simple function. It's just a constant times the max function. It's called, if you're not familiar, it's called the tent map. It gets interesting when you add a feedback loop. So it looks like this. And here we've drawn for mu is less than 1. This dotted line here, the diagonal one, is x equals y. And if you put the output into the input repeatedly, it's stable and decays. But as mu evolves, you can get periodicity or even completely unpredictable behavior. And that was a very simple function. Here's what its bifurcation diagram looks like actually for the parameter space. A more complex function looks like this, which is what we just saw in the video, where you have speech recognition going into a dialogue system and the synthesis. You have complicated systems that we don't control, like the internet or the phone networks or an iPhone, all the way back through the brain and back to speech recognition. So it's a very complicated function. These feature a neural network. These have physical effects. These are stochastic. These have nonlinearity or distortion. These have information loss, and all of them consume latency budget. That's a fundamental challenge of building a system like this, especially when you don't control all the components. Nonlinearity has two, linearity has two components to its definition. The first is that you should be able to sum the inputs and get the sum of the outputs. Speech recognition is a good example of a system that is very nonlinear. So here's a recording of me saying San Jose is a city in California. Here's a recording of me saying machine learning is a statistical computing technique. If we sum the inputs, we do not get like a sum of those words. And this is true about most complex machine learning systems, especially things that are sequence systems. The other definition of linearity is that it should respond linearly to linear scaling. So here's me again saying San Jose is a city in California, but if I turn up the amplitude, even so that it's still comprehensible to a person, and the system does not respond well to that sort of linear perturbation. Stochasticity means basically unpredictability or randomness. It's a big component of a system like what you saw demonstrated. And if you do a demo with us, which we're happy to do at GTC, you will be able to see kind of how it responds to random inputs. And we really are generating a lot of stochasticity because we have two components we've already talked about. We have a transformation that is nonlinear, speech recognition, dialogue systems, NLP. All of these are very nonlinear things, as is telephony, distortion, microphones. There's a lot of nonlinear things in the path. We've added a feedback loop. Interactivity is one of them, but there are other feedback loops of various levels of stability. And our input signals come from the physical world, so there's naturally occurring noise and variance in the signals. And all this translates to a system that's highly stochastic, highly random. And how do you deal with that in a system like this, or any system of this degree of complexity, is you take that system, you wrap it up, treat it as the stochastic system it is, and you add controlling negative feedback. And so there are things at the low level, such as rescoring a lattice in speech recognition, or there are things at the high level, like when there's low confidence coming from the dialogue system or from the speech recognition, ask the user to repeat what they said. And there's feedbacks at many levels of abstraction, from interacting directly with a person and user interfaces, all the way down to how you design your model to handle perturbations in its inputs. Dropout is another good way to add robustness there. Jitter and aperiodicity. And so we operate in a very bursty environment. This is actually a graph of power usage in New England during 2 Super Bowls. And you can see there's a little bit more viewership when New England was playing in New England. But you do see a lot of burstiness, but predictable burstiness. You encounter the same thing in the call center. I don't have a real call center volume graph up here, but this is what they typically look like. On a typical weekday, you're going to see a diurnal cycle where a lot of people are calling in the morning. You might have a big burst at lunch, maybe convolved with the number of time zones that your call center serves. And then maybe on payday, it looks more like this. And so you have to be able to handle that sort of diurnal cycle bursts, unpredictable bursts. So here's a kind of a cartoon of what how you handle variable and fixed loads, some of which require CPUs, some require GPUs. There's actually a lot more fine-grainedness to our requirements for operation because we have some models that use far larger amounts of memory or have more disk I/O, and so you start to get a lot of chunkiness to your resource usage, especially when you have a large number of distinct tasks. We deal with this partially using tools like Kubernetes and containerization, but also we deal with it by trying to pipeline our machine learning artifacts in a way so that reusable things like word embeddings or spectrograms can be shared across models. And that sort of pipelining, if you've studied queuing theory, you know that there's a very fine change to how your queuing topology operates, can have a really big impact on efficiency and throughput, and this is no exception to that. And there's a fundamental trade-off, and anyone who's worked on interactive systems knows this, between jitter, latency, and efficiency. We could highly over-provision our system, but lose efficiency. We can have lots of buffers for different types of jitter and bursting, or be over-provisioned there as well, but that will cost us both efficiency and latency. And so you have to find the sweet spot, which is at the limit of human perception, which Alex will talk about a little bit more. And that's also at the limit of what you're willing to spend on resources. And finally, scale, which a lot of people I'm sure will be talking about at GTC. Obviously very important for us. We deal with hundreds of millions of calls a year. In machine learning, the goal obviously is to take a function and to approximate the function in kind of a parity of itself that uses less resources to achieve what it maybe is an unobservable function in its entirety. The naive, I think, thinking about how do you build a product or a company around machine learning is you wrap up your function and then serve it through an API in its raw form. But in reality, when you're building an interactive application that serves end users, that is highly configurable, that has a lot of components that are not learned components, it looks more like this. Where you have large numbers of services that are an amalgam of learned and unlearned systems. And in reality, you have different types of resource utilization that you have to optimize for. You can have subcomponents die. You can have subcomponents lose message queuing or communication. You can have data stores that go out. And you have to be able to deal with all those. And when you have a system that's very nonlinear, already is very stochastic, you have to account for those sorts of failure modes in how your learning system is going to behave. All right, so I'm going to hand it over to Wonkyum Lee, our lead speech engineer, to talk about a case study in closed feedback training on speech recognition.
All right. Thanks for the introduction of our talk, Anthony. Okay. This part, I'm going to talk about how the closed loop feedback helps the speech recognition task. And well, in the speech recognition task, we have three major challenges as well. And the latency generally is like how long it takes to respond to the speech signal, but here I want to say latency. Also, we are caring about how quickly you can adapt your system to your environment like that. So that's about it. And so generally, the speech recognition is a task of the converting from speech signal to text. So it's kind of speech to text task. In generally, speech recognition has roughly four sub problem like signal processing and language modeling and pronunciation model and acoustic model. Recently, people are working for this as with the data-driven model. So, and sometimes people come up with the one model that can handle all the different things in one model. But conventionally, people are focusing on each submodule to optimize towards a specific metric of their problem and then combine into one model. That's the current state of speech recognition system. And the speech recognition has been studied for decades, actually, but until 2010, its accuracy was not as good as for the practical application. However, as a deep learning surge and a lot of the computation efficiency, we are able to improve a lot of the speech recognition accuracy with the data-driven model. Especially in the one academic task, in the switchboard task, we are getting around the 5% word rate task. So the decreasing error means that you can get more high accuracy in the speech recognition system. And behind this success, there were data boost. People are using more data, and also behind the data boost, also people are enjoying the computation boost. Actually, NVIDIA GPU contribute a lot to this deep learning and machine learning society. And also with the data boost and the computation boost, also scientists or the researchers are working toward how to architect the deep learning model for speech recognition task. So the left side was like 2012 model, like just a multi-layer perceptron, a simple, fully connected network. And then recently, people are coming up with time-delayed neural network or some kind of the scheme neural network that can model the sequential characteristic of the speech signal into one neural network. So with this model boost and data boost and the computation boost, people are enjoying a lot of improvement of the speech recognition system. But still, there are a lot of challenges because in each application has different language. I mean, some people people speak differently in commercial system, contact center, call center, or sometimes people speak differently in their podcasts, like news broadcasts like that. So there's specific domain term in your application, so it has to be addressed in speech recognition system. So one model may not optimize toward all the different domains. So this has to be studied as well. Also, people are speaking very differently in terms of the acoustic side. So people in GTC also people speak English, but their English are very different from their mother tongue language or their dialect like that. Also, sometimes in contact center, we often see like people are speaking at some emotion status, and then it sometimes leads very challenging in terms of speech recognition accuracy like that. So with this, all the challenge actually is impossible to learn everything before we service the speech recognition system in the real world. Because there are a lot of diversities and variabilities in the real world speech. So before how to tackle this problem, before we dive into this problem, let's think about our deployment cycle of the speech recognition system. Generally, before deploying the system, we perform the kind of the data generation process as well. It means that we need to collect all the good data to train the model. Once we have data, we can train model, and then once we are confident with that model, we can deploy that model into production. And sometimes we keep iterating this cycle to improve your system. But generally, I want to say that the data collection process is mostly kind of the bottleneck of when you build, perform this cycle, because the data collection involves a lot of human effort, and also since that it takes a lot of time. Sometimes it costs a lot of money as well. So I want to focus on how can we reduce this process? How can we reduce time and cost like that? So we can look at the data. The LED data is like supervised data. People are using mostly when you build a speech recognition system, you should have some supervised data. Currently, the switchboard and reverse speech are the kind of the popular data set in the academia for the benchmark. They have like 300 hours and 1,000 hours of speech data. And also in the commercial company like us, we collected like 30,000 supervised data. It's great. It's very good start. But if you look at the unsupervised data, as Anthony said earlier, last year GridSpace processed the 2,000 years of speech data. So it's a lot. So this graph is actually the low scale, but if you see in the linear scale, comparison is not meaningless. Meaningless. So unsupervised. There is a lot of the unsupervised data, and if you come up with some good way to exploit the unsupervised data, it should be very helpful to your organization. So the one way is the semi-supervised training. So semi-supervised training means that we take the unsupervised data, but we use our model to get the label. So it's kind of the you use hypothesis as the kind of label. In the speech recognition task, semi-supervised training, for that we can use our seed speech recognition model to get the transcription of that audio. And with that, we can perform kind of supervised task as well. And however, if you use all the unsupervised data with your machine transcription, in my experience, it would harm your model as well, because the one very bad data can, or some of the 10% of your really bad data would kill your model parameter as well. So sometimes you need to come up with some data selection method you might need to look at some heuristics based on your knowledge about your application. In our contact center application, we see that confidence score and length and topic speaker information would be kind of good metric to look at how to filter out some data as well. So we have been using that metric. And for this, the task of the semi-supervised training, you can look at this diagram. And if you have the unsupervised data, you can use your seed model. Here in GridSpace, we are using the Kubernetes cluster of the speech recognition system. And we can transcribe the thousands of hours of speech signal in 1 hour. And once we get machine transcript, you can follow the data selection or data weighting, or we can also correct with some heuristics method as well. And after then, we can get some training data. So with that data, audio and transcription pair, you can train acoustic model and language model in your GPU cluster. And with this process, also you can evaluate your ASR or your speech recognition system with your evaluation data set. And then once it is good, you can keep deploying the model, and then you can keep iterating this cycle as well. And so once you have seed model, and you can, if you use semi-supervised training with your unsupervised data will come from your streaming data of your service as well. And then it could learn a lot of the variabilities and also different language as well, and new language as well, and also so it can adapt to your new real environment system. So day by day, it will be better learner. So when we experiment with the semi-supervised training with the NVIDIA GPU, P100 can process like almost roughly over 10,000 hours of speech data. Also, B100 it can process roughly like 14,000 hours of speech data. So if you have dozens of the GPU cluster, probably you can process all the kind of the 100,000 hours of speech data over your unsupervised data, and then you can make the speech recognition system better day by day with the semi-supervised training. That's our plan as well. And this is kind of the one snapshot of our experiment result. And so unmatched domain means that we have this general model, or when you deploy the general model, it performs at the 14% error rate in our contact center. And supervised training means that actually we also hired some transcriptionists to transcribe some hundreds of hours of speech data. And then the word error rate goes down from the 14 to 9.5, which is great. But as you see, the system building hours was like 3 months. Mostly, it takes a lot of time in collecting the data set. And yeah, but however, when we with supervised training model with the matched domain speech recognition system, we are able to perform the semi-supervised training, and the word error rate goes down from the 5.9 to 7.8. I want to highlight that semi-supervised training here it takes less than 1 day, which is great. And also we can train every day, and we can make better model. Yeah, this is about the semi-supervised training, and the next one is like our TTS case study.
Thanks, Wonkyum. So I'm going to talk a little bit about stochasticity and latency in our text-to-speech model. So the exact inverse of what Wonkyum is trying to do. And I guess first, I was thinking a bit about what we want our system to achieve. So when someone is talking to this system, we want them to think, yes, this bot understands me, I can talk to it as I would a human, I'm comfortable, I'm not frustrated. And how do we achieve that, and how do we evaluate that? So I tried to boil it down to three different evaluators here. So we have content, naturalness, and the cadence of the conversation, all of which are very important. Content can't do much about in terms of the TTS. Obviously, if the dialogue system says something illogical, or even if it says things in an unnatural kind of robotic way, that can seriously impact how much you think you're talking to a human or how much you enjoy talking to the dialogue system. So I'm going to focus on naturalness and also the cadence of the conversation, which through latency, TTS can affect. So what does our TTS system look like? Well, we use a modern neural system. So we have text going in at the input. We have a neural network that transforms it into a spectrogram. And then that spectrogram is transformed by a different model into the waveform. And we like these models because they give the best naturalness of any TTS system out there. And they're also more controllable if you want to condition them on things or you want to modify the prosody, which I'll talk about in a second. So this is what the first part of that model looks like. This is typically called a Tachytron style model, from the paper which came out a couple of years ago. And basically you have your text going in at the bottom there. It goes through a neural network, I'm simplifying a bit here, and then into a decoder. And that decoder, frame by frame, is going to auto-regressively generate that spectrogram. And at least in our system, that has all the speaker information, all the prosodic information. So really, all of that is encoded in that first part of the model. And then we use the other model, which is typically a WaveNet style model, to take the spectrogram into that audio which you hear. So how does stochasticity fit into this? Well, if you're talking to one of these systems, our dialogue systems aren't always perfect. Sometimes they say things over again. They say something very similar or the same thing again. And what we can do is we can actually inject stochasticity into this model. And what that allows us to do is have it say something different every time it runs through the model. So here, for example, something you actually do normally in training is you would drop out each of the frames as they go into your decoder. And you do that actually mostly because it makes training more stable and you're less likely to overfit. But actually it'll mean at inference time, if you leave it on, you get something different coming out of the model every time, which is useful. You can actually do more explicit modeling of this, which is something we're working on right now. There's a recent paper from Google that came out about this. But essentially, you can actually inject the spectrogram into the model with the text during training. And then you can use a VAE system, for example, to, in an unsupervised way, extract prosodic information from that spectrogram. And then when you go into sampling, you're both sampling from a model, and you can also explore that latent space and produce perhaps something which someone is speaking faster or more softly. We actually find it's useful when someone is looking up something in the TTS system to have almost an under-the-breath kind of prosody, so that you can expose using this kind of system. So the next thing is cadence. So the cadence of the system, the TTS, is really going to only affect by how fast it is. And this is really crucial. So there's latency. If you're talking to a bot, right, and you say, can I transfer some money? You wait a beat, and then maybe you say, hello, nothing has come back. Suddenly the bot comes out with, how can I help you? But now you've already said hello, and the bot is confused, so it waits a bit more because it has high latency, and then it says hello, and you get angry because you've got nowhere and you're just looping. And this is something which we really want to avoid at all costs. So really, there have been various studies from telephony providers about this, among others. It's pretty imperceptible if you have latency in the range of 0 to 150 milliseconds. Up to half a second, particularly in a call center type setting, that you can kind of get away with that, particularly because people are already trying to complete a task. But if you get any higher than that, it becomes really difficult to use the system. So we're going to try and reduce that as much as possible. Most of the latency, or at least the most challenging part in the last year or two to get the latency down, has been in this second model, which is from the spectrogram to the waveform. Typically, you use a WaveNet style model. This came out in 2016, and it's kind of the standard for modeling sample level audio now. The trouble with it is that at inference time, it's it's autoregressive in its naive form. So basically, although you can train it in parallel because you have all the data, at inference time you have to generate a single sample at each time step, which is very slow and hard to optimize on a GPU. Thankfully, there's been a lot of good research in this direction to have a parallel version of this model, culminating with a paper NVIDIA released recently called WaveGlow, which essentially allows you to have parallel training and parallel inference, the best of both worlds. But even once you do this, it's still advantageous to get more latency gains. So we've been exploring using the TensorFlow and TensorRT integration, which came out, I think, just before GTC last year. And what it allows you to do is take your big, messy TensorFlow graph, this is just looking at it in TensorBoard, and compile it using TensorRT to a very efficient operation. This is the code right here. It's very simple, just a couple lines, and you end up with a much faster TensorRT model, which can go at 1.4 times the speed of your first model. And we found no degradation going to FP16 here. And then you can actually go even faster. So TensorRT has in-tape calibration built in, so you can actually reduce the precision of your model even further. That looks like this. You just add a couple lines of calibration, and basically what this is doing is it's figuring out how to scale each of the layers into in-tape layers. And then you get even faster, so we could get another 1.7 times boost, and you can see suddenly that latency is getting closer to the acceptable region. You do see a little bit of audio degradation at the moment with this, but we're working on calibrating it a little better, and hopefully that'll go away. And then deployment is just in GKE with TensorFlow serving, which supports all this stuff out of the box, which is nice. And yeah, so I mean, we've explored all of these different components of the system, and it all enables the demo, which we're really proud of, and which hopefully is getting better fast. Thanks to everyone for coming. Thanks to NVIDIA for hosting us. If you want a demo of Grace to see it live just from your phone, come talk to us. If you operate a call center, come talk to us. Or if you need processing or automation, you can email that gtc@gridspace email address. And also, if you're interested in working for Gridspace, you can email hiring@gridspace. We're always looking for great engineers and machine learning people. So thanks.